Hello, my name is Leo. Today we're going to talk about cryptography. Cryptography as the name came from the Greek words kryptos meaning hidden or secret and graphein meaning writing. The term which is interchangeably used is cryptology. Cryptography is a branch of mathematics and computer science whose main aim is to hide recognizable form from the original message to some unrecognizable form of the same message content using some cryptographic algorithm in which is included some cryptographic function. So first we have some sender, the person who sends plain text, which is text in a recognizable form. This plain text goes into encryption process in which it is encrypted and we get ciphertext, unrecognizable form of the same message, received by receiver, and at the same time is performed cryptographic hash function with which we got hash. We are going to talk more about. The inverse process of encryption is called decryption. For both encryption and decryption process is needed key. Key can be either symmetric or asymmetric. Symmetric key was mainly used in traditional cryptography, while today is more used asymmetric key. Symmetric key is the secret key only known by sender and receiver and is used in both directions for both encryption and decryption process, while asymmetric key is actually two keys, public and private key. So public key is used for encryption and the private key for decryption process. We have process of cryptanalysis, which is similar to decryption process, but cryptanalysis is actually breaking ciphertext without knowing key in advance. So first we have to find cryptographic key and then decrypt. One more thing which is very important to emphasize is the difference between code and cipher. Code mainly bases on meaning, semantics of some word. So codes, for example, Morse code, is some shortened expression for some word or sentence with the same meaning. We can find, for example, code books, which are books where we have that kind of word or a sentence and its code with the same meaning. And cipher actually bases on symbolic, so on symbols, which is syntax, and it is used, so it is gotten by encryption process in cryptography. Cryptographic hash function is a normal hash function, meaning that it has as an input arbitrarily sized input called message, which goes into cryptographic hash function, and as output we get so-called digest or hash value, which is here presented in hexadecimal form. So it is easy to get hash output from the original message input, but it is very hard to get the original message from hash output. There is a property of avalanche effect, which is especially used in avalanche test using for testing if there has eventually happened some error during data transmission or storage in input, which would result in significant change of hash value output. So cryptographic hash function is used in cryptography and for saving message integrity in authentication process and also for digital signatures. And digital signature is kind of proof, kind of signature that message came from the particular sender source it claims to be sent from. So it is kind of reliability proof. Data encryption use case. Data confidentiality. Let's take example of man in the middle, which is a person which appears between sender and receiver, who can intercept data between sender and receiver and read confidential information if they are not encrypted. If we encrypt this information, man in the middle will read cipher, but will not be able to understand this data without knowing secret key. Here we have examples of confidential information, such as personal identification information, information about our payment card, and especially is used this data of confidentiality use case in top secret agencies and institutes, such as in police, military, and so on. We have example of radio communication system, TETRA, European system, which is now spread all over the world, which is used, for example, in police. Let's take example of two policemen who are conversating via their walkie-talkies, and this is private conversation which cannot be heard by any other listeners. Data integrity. Let's take example of man in the middle. So here man in the middle again intercepts data and can read information, but in this case information are not confidential, so we are doing hash of data to prove data integrity. In this case, man in the middle tries to change data on their way to receiver, and the receiver will recognize that hash does not match the data and will refuse to accept this data. This data integrity use case is very useful in, for example, internet games. So when we have computer gamers who are playing via internet, we have, for example, a computer player who has some character. And if he or she makes some movement with that character, then this movement has to be equally presented on all the other computers of all other computer players who are playing that computer game via the internet at that moment. The second example are web pages. So their design, their organization is also an example of consistency of data integrity. The one-time pad. The one-time pad is the strongest possible encryption technique. Firstly, because of randomness. So its input is truly random. It is some message, for example, a 3-letter message. Let's take message ABC. Then for each of these letters is randomly generated some shift for which these letters will be shifted in order to get some other letter in output. And more about these shift cryptographic systems we are going to talk in one of the next presentations about cryptography. But what is important to say, then for each of these letters can be generated one of 26 shifts, because the English alphabet has 26 letters. So the whole number of combination for 3-letter message is 26 times 26 times 26. And we can conclude that for the longer messages, this number of combination will be even bigger. And the frequency stability is the other main property. It says that it is equally likely for output to contain any sequence of any length. So we know it is related with the property of every language. For example, in English language, the most frequent letter is letter E. And also are known frequencies of other letters, so that are approximate frequencies of letters used in normal everyday conversations or any other way of expressing in particular language. And using the one-time pad encryption technique, we get in output uniform distribution of frequencies. So almost all letters have approximately the same frequency of being appeared. In the one-time pad encryption technique is used XOR bitwise operation, and bitwise operation is operation done on some 2 or more, let's take example of 2-bit arrays, which are arrays of bits, 0, 0, 1, 1, 0, 1, 0, and so on. And XOR bitwise operation is very useful for this one-time pad, because it has as output, when we have 2 inputs, it has as output equal to 0 in 50% of cases, and output is equal to 1 in the other 50% of cases. So this 50% probability also contributes to the one-time pad concept, to this encryption technique. People throughout the history aspired to automate the one-time pad encryption technique, so there were built the first encryption machines. An encryption machine should have worked on the next principle. So in the input was some message, and that message consisted of letters. Each letter in input was shifted for some randomly chosen number. And in output we had that message consisted of letters which are shifted for that randomly chosen numbers. And the second important property was to have the scrambled rather than repeatable patterns. So there actually it wasn't actually any pattern. But these two properties could not and today also cannot be realized, because we know that any machine, including encryption machine or today's computers, cannot generate perfectly random numbers. So in the history, for example, in the last century, two people, sender and receiver, wanted to exchange some message on their encryption machine. The first pre-requirement was to have the same machine. Then they had to agree on the identical initial configuration called key setting. And a set, so combination of all possible key settings, is called key space. Then they had to align their machines to the same start position and finally do the same set of operations to get the wanted encrypted message. One of the first encryption machines was the Enigma cryptographic encryption machine, which was designed after the World War I in the 1920s. So it consisted of rotor machines, which are machines which consist of 3 or 4 rotors. Here you can see 3 rotor machine. So there were first 3, but later they expanded to 4-digit rotor machine, so as to have greater number of combinations, greater number of key settings, so bigger key space. And so we have some rotor machine. In input was some letter from an original message. It goes to input, then it sends some electrical impulse, goes through the certain electric pathway, and in output we have that number shifted for randomly, actually pseudo-randomly generated number for shift. And here are the two main reasons why the principle of the Enigma machine work was discovered. First, because lots of workers who were working on the Enigma machine weren't so randomly choosing their inputs. So there was each time very similar key setting before the beginning of the Enigma machine work. For example, they changed only few or each of these digits or each of these rotors in rotor machine, but only for few numbers up or down. And the second very big error was design error. So Enigma machine was designed in this way that, for example, the letter E could never be letter E in the output. So it was actually a weakness rather than strengthness. And because of these two reasons, the known plaintext attack, KPA, was realized. So it is an attack model for cryptanalysis. The Germans had their opposite side in the World War I allies, and they did this KPA attack using common words from the German language. It's called plain text or crypt words, so these original messages, and their encryption ciphertext. And using these two, ciphertext and plain text, they can get known the key. And in this way was discovered the way of that Enigma encryption machine worked. Here are two types of data secrecy, which is way how to keep data in secret. The best type is perfect secrecy. So here we have message space, key space, which is space set of all possible key settings, and ciphertext space. All of them have the same size. If we choose exactly one message from the message space, one key setting from the key space, and then we get exactly the one ciphertext from the ciphertext space. Random generators are generators on which perfect secrecy is applied on. They have as their input, truly random parameters, such as, for example, parameter used from some natural phenomena, for example, activity of some radioactive source. And they are non-deterministic generators, meaning that their output cannot be determined on any basis. The only way how can we only predict but not determine their output is by guessing. Pseudo-randomness, also called fake, pseudo meaning fake randomness, is the type of randomness which is applied on machines generating numbers, also today's computers. And these are deterministic generators because their output can be determined on some factors, for example, principle of their work and so on. ENIAC was the computer on which mathematician John von Neumann, who was working on design of hydrogen bomb at Los Alamos, he wanted to repeatedly calculate some approximations of processes involved in nuclear fission on the ENIAC. But since ENIAC had limited internal memory, it couldn't store such a long sequences of randomly chosen numbers. So he came up with a idea of middle squares method, which was one of the first modern cryptographic methods. And here we have in input, for example, number 1, 2, 3, 4, take its middle, 2, 3, then square it, then take the middle of the new number, square it, and so on. This is why it's called middle squares method. Random input is input such as the current time expressed in milliseconds, so to be precise and have the bigger number of combinations, or noise measured at some moment. But it is random input. However, we know that computers generate pseudo-random input, and this input is called seed. The longer the seed is, also is the longer period, and period is length of time before the one cycle repeats, and cycle is some time for which outputs begin to repeat. For example, we have output cycle 2314 and then again 2314 and so on. Practical secrecy rather than perfect secrecy is what computers deal with. So practical secrecy is when, for example, some person has some encrypted ciphertext, but he or she does not know the key. And it would take him or her the hundreds of years to decrypt it because that person does not have key. So it is practical rather than perfect secrecy, because it would mean hundreds and hundreds of years, which is not a reasonable time to decrypt that encrypted message to the plain text. And today's computers are faster and faster, have a bigger and bigger storage, so they can work much more. So the length of this seed must be bigger and bigger. In this video, you've learned what cryptography is, about its importance in use, and got a picture about cryptographic concepts which are desirable to have in different parts of encryption process. More about both traditional and modern cryptography systems and algorithms they work on, you're going to learn in one of the next videos about cryptography. Thanks for watching and stay with us.